Okay, so welcome to class. We're talking about exponential functions. They're a brand new type of function, nothing like polynomials or rational functions. They have sort of their own property. And one of the really cool things is that they're used all over business and finance. So let me give you sort of just a quick example of something that we've been toying around with here at the beginning of class, those students that showed up a little bit early. So let's say that you're a bank, right? Let's say you're not borrowing money, but maybe lending it out. So let's say you lend out $1 to somebody. Maybe it's not a friend, right? So you just want as much money back as you can get. And they're a terrible sort of investment, so you charge them 100%. But it's just every year, right? So every year they got 100% interest. So they got to pay you back $1, but they've got to pay you back more as well, right? 100% interest. So how much do they owe you after 1 year? It's the original $1 plus how much more? How much do we owe total? Yeah, it's $2, right? It's the $1 plus 100% of what you owe. So $2, right? Okay. What about after 2 years? After 2 years, indeed, it'll be $4, right? Why? Because now you owe $2 after the year, right? And then you have to pay interest on that $2. So you have to pay the $2 that you owed after the first year, plus 100% interest on that $2, which is now 4, right? 2 times 2. And notice what you did to go from this value here down to this one, right? It's $2. And remember, initially, the original value was 1. So to go from 1 to 2, you doubled. So what about on the third year, right? What would you owe after 3 years? Yeah, it would end up being 8, right? And so what we're seeing here is what's called exponential growth, right? And this is typically what a banker will do. This is called compound interest. They tell you how many times they're going to compound the interest and by how much. And what that tells them is how much they're going to multiply your money by, or how much you owe at any given instance, right? And you'll take out a loan for a certain number of years, and then they'll use these sort of calculations to figure out how much you owe after a few years. Or you might make an investment, and that's how much they'll have to pay you after you make that investment, right? But what we're seeing with this is this sort of multiplicative factor. And this is what we should be sort of aware of with what are called exponential functions. And it's one of the reasons why it shows up all over the place, sort of in nature, and then also in business and finance. Chapter 6 is going to be all about exponential functions and their inverses, which are called logarithms. But today we've got 4 main learning objectives that we're going to hit. The first thing that we want to do is just talk about evaluating exponential functions and this idea of this multiplicative factor that I'm talking about, right? How much you multiply by. And that previous example, we were multiplying by 2. We'll often call or refer to that as the base of the exponent, right? If we increase by the input by 1, the output gets multiplied by that multiplying factor of the base. And we'll talk about how to evaluate exponential functions. We'll find sort of just the way that we did with polynomials and quadratics and linear functions. If somebody gives you some information about the situation, maybe some points on the graph, in the case of exponential, you just need 2 points on the graph, then you should be able to write down an equation for that exponential function, okay? And we'll talk a little bit about what the format of an exponential function looks like. They all have a certain format, and how you recognize when a given function is either exponential or not. And then we'll get back to what we were just sort of talking about at the beginning of class here, this idea of the compound interest formula. And so we'll look at that, and we'll talk about cases where we don't just compound necessarily sort of once a year, but twice a year or 3 times a year or every single second. And eventually we'll get to the point where we compound what's called continuously, and that's at all instances, so infinitely many times. The nice thing, though, is that we don't charge the full interest rate. When we do that, we have to sort of divide by the number of times that we are compounding, so there is a nice interplay there. And then the last thing is that it turns out that when we do this sort of compounding continuously or infinitely often, then, or charging the interest infinitely often, then we naturally run into one of the most sort of interesting constants, similar to something like pi in mathematics. It sort of plays a role in a lot of exponential functions. It's Eulers constant E. And before the final exam, you should make sure that you're familiar with how to find E on your calculator and how to raise E to various powers, right? So make sure you know how to find that before you get into the final exam. Okay, and then in section 6.2, we'll talk more about the graphs of these exponential functions and sort of the key features, and then we'll get into their inverses, which are called logarithms, and some of their applications. Okay, so there are some key words that you'll end up seeing. The first is that you'll often hear things talked about in terms of percent change, as opposed to this multiplying factor. So the multiplying factor, the amount that you multiply by, is called the base. But they often won't refer to it as the base. They'll talk more about what's called the percent change. And the idea is that, you know, if you have some sort of fixed value, you multiply by 10% and you increase the value by 10% or something like this. So you have to be aware of when they're giving you the increase in terms of percentage or in terms of that base number. If it's in terms of percentage, you'll have to convert it back over to a base, right? So for example, 25% would be something like 0.25. That's the multiplying factor of 1/4. Okay, so that's something to be aware of. And anytime you see a percent change that's based on the original amount, you should sort of think, well, this is probably either some sort of exponential growth or some sort of exponential decay. Now, there are two possibilities when you are multiplying by one of these factors. So, for example, in that one that we started with, we were multiplying by 2 at each stage, and so we were sort of increasing the value of the function by a multiplicative factor, and it was increasing. And when that happens, we refer to it as exponential growth. And that's going to happen anytime that base value is bigger than 1, because if it's bigger than 1, when you multiply it by that number, it will grow. On the other hand, you could have a base that is a number that's less than 1. For example, maybe you're multiplying by 1/2. In other words, you're cutting the amount by 1/2 at each stage. And this happens, for example, if you have some sort of bacteria or something, and maybe there's some sort of disease in their environment or something in their environment that's killing them off. And at each stage after, you know, a given cycle, maybe a day or 2 days or something like this, the population is cut in half, and then cut in half again and again and again. And in that case, the multiplicative constant would be 1/2, and since it's decreasing, we call it exponential decay, right? Okay, so the hallmark of exponential growth or decay or exponential function is this multiplicative factor that we're calling the base. If it's bigger than 1, it's growth. If it's less than 1, it's a decay, and you should be careful about how they specify it. Sometimes it'll be in terms of a percentage. And I'm just going to leave this up on the screen for a few moments, and if you're sort of taking notes, maybe you can give me a thumbs up as soon as you've gone through all the details or you're able to read through this. And if you have a question, you can also ask at this point as well. But just a little bit of terminology with what's going on, right? The difference between growth and decay. And one cool thing to take away from what we're saying here is that if we look at the graph of an exponential function, it's always going to either be increasing or decreasing. So it's going to be very different from our rational functions or quadratics or polynomials where, you know, you can go from increasing to decreasing and have one of these humps. For exponential functions, they're either always increasing or always decreasing. Okay. So let's become, you know, or let's look at one that's a little more concrete, and it's basically the same function that we were looking at before, but I want to compare it and contrast it to another type of function that we've seen in the past, right? And to maybe try and understand the difference between the two types of growth. So the function on the right is g of x, And in that case, it's a linear function, and we're multiplying by 2 here. But in this case, it's not going to be exponential. So let's talk a little bit about maybe why it's not exponential. It's linear, and it has a slope, right? So what is the slope in this case? What is the rise over the run? Okay. What do we got here for this linear function? So I've got somebody saying 2, a couple of students saying 2. Yeah. So here it's whatever's in front of the x. Remember, the y-intercept of this linear function would be 0, right? The b was 0 for that mx plus b formula. And we typically will write this as 2 over 1. So we'll think about it as the slope is 2, but we write it as 2 over 1. And we sort of previously had said that, the slope tells us the rise over the run, right? And what this means is that if we move to the right by 1, then we're going to go up by 2, right? So to the right by 1, up by 2, to the right by 1, up by 2, to the right by 1, up by 2. And to go up by 2, all you're doing is adding 2 to the output, okay? So here, when x is 0, when the y-intercept is 0, and what we do is every time we increase by 1, the output increases by 2. So we just add 2 here, boom, and then we add 2 here, and add 2 here, and add 2 here, and add 2 here, and just continually add 2, and we increase by the exact same amount at each instance, right? And this is what's meant by this rise over run. On the other hand, with an exponential function, they're all going to look more like this, like a 2 to the x here, and the unknown or the input to our function will be up in the exponent. And they sort of rely on the fact that if you look at 2 to the x plus 1 and think about the sort of properties of exponents that we've talked about in the past, this is the same thing as 2 to the x times 2 to the 1. In other words, it's 2 times 2 to the x. So if I increase x by 1, if I run by 1, then the output here gets multiplied by 2. And you can see that in this picture here. We can multiply by 2. There's that multiplicative factor, 2, 2, 2, 2, and 2. And so this 2 that you're seeing here is called the base, and that's that factor that we're multiplying by 2. So for linear growth, at each stage, for equal increments, you increase by the same y value. And for exponential growth, as you increase for equal increments, you multiply by this base factor. And that's what's being said here. So exponential growth refers to the original value from the range is increased by the same percentage over equal increments found in the domain. So another way of saying this is it's just multiplying by the same amount. Whereas linear growth refers to the original value from the range increasing by the same amount every single time, right? So you're not multiplying by something, you're not increasing by a certain percentage, you're just increasing by the same amount. And so that's what's going on here. We've got one case where it's a linear function and the other where it's exponential. And so you can see, for example, here that the linear function is definitely not something that's exponential, because the hallmark of an exponential is that you're multiplying by a given factor. And they all look like this, okay? So every single exponential function that you'll have has this sort of standard format. We'll also talk about another one when we introduce the Eulers number, which is E. But for now, if you fix two constants, A and B, then you'll end up with a exponential function, right? So just like when you're looking at, for example, ax squared plus bx plus c for a quadratic, you think about the a, the b, and the c as being sort of fixed numbers. Here the x is the variable or the input into our function in this case. So there are a few things that you need to know about these two numbers, a and b, for it to be an exponential function, because not every choice of a and b will give you an exponential function. There are some that sort of botch things up. So the first thing that you have to know is that a can't be 0. and the name for this constant a is called the initial value. And it turns out to also be the y-intercept. And the reason why is that if you take 0 and plug it in for x, you get f of 0 is equal to a times b to the 0. And b to the 0 is just 1. So this is a times 1, which is just a. So this is saying the point 0a is the y-intercept. And so we often will call it the initial value, right? So it's what happens when the input function here is 1. And you can see that down here. So this last bullet point here is just the y-intercept is at 0a. Another thing that will always happen, and we'll talk a bit more about this in section 6.2 on Friday, is that there will always be a horizontal asymptote at y is equal to 0. Okay? So either as you go out to infinity or out to negative infinity, one of those two directions on the graph will get closer and closer to 0, and it just depends on if it's exponential decay or exponential growth. But there will always be a horizontal asymptote. Okay, so the a is non-zero. It's called our initial value, and often you can just pick the value of a straight from a graph if you can read off exactly where the y-intercept is, right? So if you can see where the y-intercept is from an exponential function graph, then you know exactly what a is. So on the other hand, the function b has some important properties that we need to keep in mind as well. First off, it has to be negative. It has to be positive. And the reason why it has to be positive is because a function like this, f of x is equal to negative, say, 2 to the x, is going to be undefined for a lot of values, right? So, for example, if we look at negative 2 to the x, when x is 1/2, that's going to end up being a complex number. And you can sort of really see that if you check out Desmos and try to graph something like negative 2 to the x. So let's look at sort of negative 2 raised to the power of x. And I guess it doesn't even really come on as the graph for us, but maybe if we call it f of x. And you can see that if sometimes you plug in something like 1, you can get something like negative 2, you can get an output, but something like f of 1/2 becomes undefined. And so here, we won't allow for the base to be something negative, because if it's negative, it's something other than an exponential function. And that's primarily because the domain ends up really being sort of botched up. And if we keep this restriction that b is positive, we can be assured that the domain of any exponential function is just all real numbers, okay? So if we throw out these ones where the base might be a negative number, then things are a bit more straightforward and the domain is all real numbers. And so we'll keep to that situation. And then we also have to have b not being equal to 1. And the reason why we don't include the case when b is equal to 1 is because when b is 1, we just get a horizontal line, which is not really considered an exponential function. Instead, it's just considered a line. And that's because the function looks like this. F of x is equal to a times b to the x, or a times 1 to the x. And then 1 to any power is just 1, so this is just going to be a. So the output of this function will always be a, and so it'll just be a horizontal line. So when the b is equal to 1, we don't include that as an exponential function. Destiny, it can't be negative, right? So like I was saying, that's what it means for b to be positive, right? We're sort of including the fact that b has to be positive, and that's because something like negative 2 to the 1/2 is undefined. So even though it may look like a exponential function, if that b ends up being negative, then it's not exponential. Okay, so you can think about the a out here in the front as just being sort of a factor that stretches or squeezes or flips it across the x-axis. And as we look at 6.2, a little more detail, when a is positive, the function f will always be positive, and when a is negative, the function f will always be negative. So we'll see that again in the next section. Okay, so here is an example of sort of some questions that we'll see in the Edfinity homework. And I'm sort of bringing them both up because you have to be a bit careful about the wording. Notice that this one up here says which ones are not exponential, and this one down here says which ones are exponential. And I'm going to give you a few moments to think about which ones you think are exponential. There are a couple here that are obviously not exponential, and I'll go through and highlight the ones that are not exponential in this case, and then we'll go on to the second one and highlight the ones that are exponential. But my point here is just to tell you to be careful about the wording, right? Carefully read what they're asking you for here. But we'll think about that first set up here on the top. There are a couple here which are obviously not exponential. So if you see one of them that's not exponential, go ahead and put it into the chat, and we'll talk about if that's the case or not. So which of these is not exponential? Okay, so somebody's pointing out that j of x is not exponential. Does anybody agree? Is j of x one that's not exponential? Okay, but why is it not exponential? What's the problem with this guy? I mean, it looks like something raised to the power of x. Yeah, the base in this case would be negative, right? So this is exactly the question that was being asked before. The fact that there's a -2 here, that the base would be negative, means that this indeed is not an exponential function. However, h, on the other hand, is exponential. The base there is just 1/3, and that is positive, and it's raised to a power of x. On the other hand, let me ask, the base is 1/3, but what is the value of a? What's that y-intercept at? Because remember here, the format for these guys is a times b to the x. So in this case of h, what is the a? The b is 1/3. Yeah, so if you don't see anything out in the front, the a is just going to be 1, right? And you can also figure it out by plugging in x is 0, and 1/3 to the 0 would be 1 as well, right? Because it corresponds to y-intercept. So this is an example where the base is 1/3, and that a value is 1. And notice that because this base has a value of 1/3, that means that you keep multiplying by 1/3, and so this is a decreasing function. So these would get smaller and smaller. The larger value of x you plug into this, the smaller this output will be. But this one is an exponential, so I'm not going to highlight it. What about g of x? Is g of x an example of something that I should highlight? Should we highlight this or not? I guess this is sort of an interesting way of phrasing what I'm saying. Yeah, thank you, Jordan, for clarifying yourself. It is definitely not an exponential. Any polynomials that you see, any linear functions that you see are not exponential, right? And a good way to sort of think about it is that the input is in the base and not in the exponent. So here the input, which is x, is up here in the exponent. And for exponential functions, they need to be up there in the exponent. Okay, so we should highlight that one because it's a polynomial. This one on the top, let me just mention that it doesn't look quite like it, but it is exponential, and we can figure out the base and the value of a just by a little bit of algebraic manipulation. So let me show you how to do that here. So here we had f of x was equal to 4 to the 3 times x minus 2. And the first thing I'll do is multiply by 3. So this is 4 to the 3x minus 6, because 3 times negative 2 is negative 6. And then I'm going to rewrite this as 4 to the 3x times 4 to the negative 6. Again, this is just one of those properties of exponents. If you have a subtraction or an addition of the exponents, you can just write the basis here and the two powers that you had up at the top. And this one, remember, when you have an exponent raised to a multiplication like 3 times x, you can rewrite this also in this way. It's like 4 to the third all raised to the power of x. And then I'm going to put this in parentheses here and switch things around so that this number comes first. And then 4/3 to the x. So here, what we can see is that the a is 4 to the negative 6, and the b is 4 to the 3, okay? So this is an example of an exponential function, and you're multiplying by 4 to the power of 3 every time. And the initial value of the function is 4 to the negative 6, okay? It's an increasing one, so because of the fact that this b value is greater than 1, you're going to increase every time you multiply by this 4 to the third. And you increase by quite a bit, right? So 4 to the third is pretty big. It's 64. You increase by a factor of 64 each time. Okay, so those were the two that were not exponential, and sometimes you'll have to sort of do a little bit of algebra to verify if it's exponential or not. And in some questions they'll ask you, what's the base and what's that value of a? And this is a good way of going about it, like what I did on the board there. Okay, so for the second one, should I highlight f of x? Yes or no? Should I highlight it? Yes, highlight it. No, don't highlight it. What do you guys think? Don't highlight it. Absolutely not. It's not exponential. It's a polynomial, right? So this is not exponential. What about g? What's the base for g? What's the b value for g there? I'm highlighting it, so I'm telling you it is an exponential, but what's the base? The base is not 1. The a value is definitely 1 in this case. Yeah, the base here is the 0.875. So it's 0.875 to the power of x. Now, is that an exponential increase or an exponential decrease? Now that you've identified the b. So we see 1 increase, 2 decreases, a couple of increases. What do you guys think? Somebody else come in. Let's get a little bit of a debate here. Some increase, some decrease. Remember, the increase or decrease of the base is based off of that value of b, and if it's less than 1, then it's going to decrease, right? So you're multiplying by 0.875 each time. And when you multiply by 0.875, you're just keeping about 87.5%, right? That's like the decimal there. So you'd be decreasing each time, okay? So in this case, because the b is less than 1, you decrease. Okay, what about h? We have a name for this type of function. I'm not going to highlight it. It's definitely not exponential, but we have a name. What do we call those types of functions? And this is good sort of practice for the final exam, because we might ask you to distinguish between this type of function and an exponential. So you'll need to know the name of this type of thing. Yeah, this is linear, right? So it's y equals mx plus b. It's definitely not exponential. There's no unknown or input up there in the exponent. And then finally, this last one, I'm going to highlight it. It is exponential. And let me talk a little bit about what the base is, because it may be confusing when you compare it to this one up here. Because down here, the base actually is not negative, even though we have that -2 there. So let me go ahead and jump to the board really quickly. And we'll talk about what the base is in this case. And we'll see that it's actually decreasing, even though that we have this 1095.6. Because of this -2 that we're seeing here, that's going to make sure that the base is actually a number that's smaller than 1. And here's why. So this is 1095.6. And you can think about it like this: raised to the power of -2, then raised to the power of x, right? So this is just some of the properties of exponents. And so I'm pulling this x all the way out to the outside. And then here, when you raise an exponent to a power of a negative, it's like writing it as a denominator raised to the positive power. And so you can see this is the base. Okay, so there's the base. The a in this case is 1. If I plug in 0, I just get back 1. So that a value is 1. The b value in this case is 1 over 1095.6 squared. And that means that this is exponentially decreasing. And so sometimes you'll see these decreasing ones with a negative exponent up here. We're going to talk a little bit more about that in terms of the Eulers Constant. So we'll see that coming up again as well. But again, here are some good examples of the sort of thing you'll see in affinity for 6-1. Okay, so another sort of thing that you'll be interested in doing is somebody gives you 2 points on an exponential function. You should be able to write down the equation. And here, this is a word problem, but it's just giving you 2 points on the graph of an exponential function. So let's go ahead and talk a little bit about that and draw a picture. So here we've got some predators, and along the x-axis, we're talking about our input being time, so that's t. And t here is going to represent the number of years after 2011, okay? So for example, when t is 1, that's 2012. When t is 2, that's 2013, and so on and so forth. And so for example, here is where t is equal to 0 would be, and that's 2011. There's 2012, 2013, 14, 15, and so on and so forth, okay? And this is measured in years along this side. And then over here, this is measured, I guess, in number of wolves. And this side we'll call n of t, okay? Because here they're asking us to write down the population of these wolves as a function of time. So they're saying something like n of t. And the key feature they're telling us is right here at the very beginning, the population is growing exponentially. And what that means is that as time moves forward by 1 unit, the population grows by a multiplicative factor, right? Whatever that base is, and we have to determine what that value of b is. Okay, so let's just break down the other information they gave us. So initially, there's 129 wolves. So when t is equal to 0, there's 129. So this point is on the graph, 0, 129. And then in 2013, there are 236 wolves here. And so here, when t is equal to 2, we've got 236. So that would be this point here, 236. And we want to find the equation of an exponential function that passes through those 2 points. And I think for some reason the camera has paused. Okay, there we are. We're back in. All right, so here we've got this guy coming back. And we're interested in the equation of this function n of t, which is a times b to the t. Okay, so we want to determine what the a value is and what the b value is. And again, this is a good example of the type of question that you'll see not even in an application problem, but they'll just give you 2 points on the graph and say, what's the formula for the exponential? And in this case, they're just looking at a predator population and sort of going through the details there. So the first thing to recognize is that they've given us the value of a, right? So right here, the fact that this is the y-intercept tells us that the value of a is 129. That's the initial population of our predators here. So this is 129 times b to the t. So that's the first piece of information we can just use from that first point. Now we can take this point and use it to figure out the value of b, right? So how do we do that? Well, when t is equal to 2, n of t is equal to 236. So the formula should look like this. 236 is equal to 129 times b to the value of 2. And now you can see that the only unknown that we have here is b. So we can go through and solve this equation for b. So your first step is to divide by 129 to get b squared on its own. And then if I want to get b all on its own, what should I do to this equation at this point? How do I solve for b here? Yeah, we need a square root. Now, normally when we take the square root, we would put a plus or a minus. But remember that when we're dealing with an exponential function, the b is positive, right? So we're already assuming that we're going to keep the positive side here, so I won't even put plus or minus, I'll just keep the positive one. And that tells us our value of b is equal to the square root of 236 over 126. Okay, and now we can write down a formula for this curve, right? The one that you're seeing here. It's going to be n of t is equal to whatever the a was, 129, and then the b raised to the power of t. And the base in this case is this square root of 236 divided by 126. And you can see that if you type this into a calculator, you would get something that was bigger than 1, and so this would be exponential increase. And so here, this is the formula that they're looking for. And the nice thing is we can now use this formula to estimate the population in further years. So if we wanted to know, for example, 5 years past 2011, we would just plug a 5 into this formula and type it in, and we would be able to determine what our model is telling us the number of predators in the population would be in this case. Okay, and we can see that it increases exponentially. I'm not sure why I put 126 there. Thank you, guys. 129, 129, 129. Thank you. Yeah. So when I divided by 129 here, I threw in a 6 for whatever reason. Thanks. Okay, so now we've got the right answer here. Okay. But again, you're going to have a lot of examples where they just give you the 2 points as opposed to giving it to you in a word problem. Okay, so let's keep going and talk about probably one of the more important formulas that we'll see today. And now what we're going to talk about is what happens in the case of what's called the compound interest formula. And in the compound interest formula, you start out with a certain amount of money that you'd like to either lend or borrow. That's called the principal. And that first example that we did at the start of class was when the principal was $1. And we looked at the case when we were compounding once a year. So in that first example, we just took n to be 1. And so what we would multiply by, what the base was the amount that we originally owed, which was the sort of $1, plus the amount of interest. And we took that to be 100%. So we were taking r to be 1 and n to be 1 as well. And so the multiplying factor, the base that we got in that example was 2. And so we were just multiplying by 2 at each instance of t. And because we were compounding our interest every single year, if we wanted to know, basically the formula after 3 years or 4 years, we would plug in the value of t here. Now, the difference here is that when you compound more often, so instead of compounding sort of just once every single year, you don't include the full percentage rate, the value of r. And that's because this value of r is called the APR, and that's the annual percentage rate, right? So it's the percentage interest that you would charge if you compounded over an entire year. But if you're going to compound more than once in a year, that's what this value of n is. So n is the number of times you compound in 1 year, how many times you collect interest, then you have to divide the interest rate by n. And that's again because the r is typically given in terms of an annual percentage rate, an APR. Okay, so this formula is just telling us that we're just multiplying by 1 plus r over n. And the reason why you get nt up here instead of just t in the case when n is anything other than 1 is that n times t is the number of times you compound in a full year. Okay? So this is our nice formula for compounding our interest, just like we saw at the beginning of class, but now possibly more times in a year. So let's just look at sort of a quick example of something that will certainly be of interest to us in terms of an example. So we've also got a little bit of terminology here as well. So again, we're going to assume that the P is 1, right? So there's no P out here in the front. So we're just borrowing $1 or lending $1, just like we did in our first example. We're going to assume that the R, the APR, is 100%, and that means that the R is going to be 1. Remember that you just want to convert whatever that percentage is back into a decimal, and 100% would be 1, 25% would be 0.25, and so that's why we have this R value of 1 in this picture here. And what I'm going to ask you to do is think about sort of how much you would owe after 1 year. So this is also when T is equal to 1 year. If you were to compound, say, just once a year, if you were to compound twice a year, 4 times a year, 12 times a year, 365 times in a year, 8,760 times in a year, once every single minute, or possibly once every single second. And so you'll see these terms come up in the homework assignments, and the terminology here is just telling you what the value of n is. So annually means once, semi-annually means twice in a year, quarterly means 4, monthly means 12, daily means 365. You could compound every hour. But remember that the interest that you're charging also decreases as well, right? You have to divide by that n, because the R value here was the annual percentage rate. Now, like we said at the beginning of class, if you just compounded once, you would have a friend that owed you $2, okay? If you were to compound twice in a year, you would not charge 100% at each interest step, but instead 50%. That's where you get a 1/2 year. And if you did it twice, you'd end up having a friend that owes you $2.25. So slightly more money, but only 25 cents more. And you could then also think about, okay, if I were to compound it 4 times in a year, right? So every time you compound here, you're going to increase it by 25%. You're going to charge 25% interest, and it's 25% because that's 100 divided by 4. You did it 4 times in a year, they'd now owe you $2.44. If you did it 12 times in a year, they'd now owe you $2.61. If you did it 365 times in a year, it's $2.71. If you did it every hour of the year, it's 2.718. Every minute, it's still 2.71. And then every second, it's 2.71. And you can see that these numbers are getting closer and closer and closer to the same value, okay? So as this value of n gets larger and larger as it goes to infinity, the amount that you owe back on this $1 investment is getting closer to whatever this number is, 2.718282. And this number shows up all over mathematics, and it's incredibly important to sort of looking at exponential functions, and so we'll give it a name. It was really heavily studied and first sort of observed by a Swiss mathematician, Leonhard Euler, back in the 1700s. And it has, again, lots of very interesting properties, and it's useful all over mathematics. It turns out that it's the limit of this function, 1 plus 1 over n to the power of n, as n increases without bound. So as n gets larger and larger, we would have written this previously as something like this, as n goes to infinity. And we'll just give a name to this number. It is E, okay? So Eulers Constant. And when you type it in on your calculator, you should get sort of an approximation that looks like this, 2.7182882. And you should be familiar with where it is on your calculator before the final exam, right? So this guy will certainly play a role on the final exam, so make sure you know where it is and how to raise something to a power of e. Okay, so why are we talking about e? Well, it turns out that any function that is exponential can be written in a slightly different form. And so you should sort of think about this as being the difference between the standard form and the slope form of a line. It's just another way of representing a exponential function. And every exponential function can be represented in this way. So let me just write a little bit about this. PE to the RT. And we'll talk about why this is the same thing as this A times B to the T. The reason why is we can think about this R times T up here in the exponent as being P times E to the R, all raised to the T. So this is the base, okay? E to the R is the base, and the P is still just the initial value. Okay, so if I plug in T is equal to 0, I still get back this value of P. And so any function of the form f of x is equal to a times b with use an input of t. So any function of the form f of t is equal to a times b to the t can also be put into this format here. Okay, and we give sort of a different name to that number r there. And for any b, you can always find such an r. So here we call that value of r the growth rate or the interest rate per unit of time. The value of p is still called the initial value, but in the case that you're talking about sort of a business application, you'll often refer to it as the principal. So it's the amount that you loan out or the amount that you borrow. And then t is the period of investment. So how long you're going to borrow that money for, or how long the investment has been sitting in some sort of account, right? So how long have you put your money in a bank account or something like this? Okay, and the reason we use an E here is just, you'll notice that we call it continuous. And you can think about it as continuous because it comes from the fact that you compound more and more frequently. And so as you let n go to infinity, this formula here, this 1 plus r over n to the n, turns into an e to the r. And here you can think about it as taking your compounding infinitely many times. So you're compounding every single second, and this is the formula that you end up with. Now it looks a little bit intimidating, but if you just know where this e is on your calculator, it's incredibly easy to use, and it's in fact really going to be important if you ever decide to buy a home or maybe purchase a car, because often you'll have to sort of borrow some money or get a mortgage where they'll charge you interest using these sorts of formulas. So let's just look at a quick example of continuous growth and how we would write down a formula. So here we're looking at a case when a person invests $1,000. So the principal is $1,000. That's the initial amount that they're investing. And they're putting it into an account, so maybe sort of a banking account. And this bank account is paying lots of interest. In this case, it's paying 10% interest per year. And so we would call that value of r, the growth rate in this case, 0.10. So we just convert that percentage over to a decimal. And we know that that's the decimal in this case because it's telling us the growth rate, right? Okay, so that's 10%. And then we know that it's being compounded continuously. So the formula looks like this. P of t is PE to the RT. So the P is 1,000. The R is 0.10. And then the T is just the input into the function. And so that's what that first sentence is telling us, that our investment has this formula if we would like to determine how much it's worth after a given amount of time. And then it's asking us to plug in a particular value of t here at the end. If we want to know how much the investment is worth after 1 year, what should we let t be equal to? Yeah, so after 1 year, that's just plugging in p is equal to 1. So we would get 1,000 times e to the 0.10 times 1. And if you type that into your calculator, you get 1,105.17 cents. Okay, so your investment would grow from $1,000 to $1,105.17. So you'd make $105.17 over that 1 year if you were to leave your money in this account, right? And this is how basically a lot of bank accounts work. Typically you won't get 10%, but something much smaller than that. Okay, and then one last example, again, where we're going to do the same thing. And as we go through chapter 6, we're going to introduce more and more about exponential functions and their inverses and their graphs. So now we're just sort of trying to recognize some of their key features. And here's another example. So we've got a fox population that we're going to denote by f of t, and it is growing at an annual growth rate. So when they say growth rate, they mean that the formula is going to be given sort of in this format, and the growth rate is this value of r. If they told you the multiplicative constant or the base, then they would have told you that value of b. But the fact that it's saying annual growth rate should be an indicator that you're going to use the e to the r. And again, it's just a different format for an exponential function, right? For every base b, there is an r here such that e to the r is going to give you back that base b. But in this case, the r is 4%, so 0.04. You just move the decimal over by 2 spaces. And then the initial population of foxes here is 20,560. So that would be the value of p. 560. Okay, and so the formula here would just be 20,560 times e to the 0.04 times t. And that's all they're asking for in this case, is what is the formula for f of t. And then, you know, other things they'll ask you for is like, what's the population after, you know, 5 or 6 years, and you'll just plug in either 5 or 6 or whatever the question is asking you about in order to determine the population based off of this model. Okay, so there's this PERT formula, one way to look at exponential growth, and then the other way was a times b to the t. The difference is this is the multiplicative factor, this is what you're multiplying by, and this is what we call the annual growth rate, and you're thinking about it as being sort of compounded continuously. So the growth rate term comes from the fact that you're thinking about interest rates. Okay, and we're officially 2 minutes over, so I'm going to stop the video and just say thank you guys for being here. If you have some questions, I'll be around for the next 5 or 6 minutes.